Starting the YouTube stream for those who are not able to join us today. So, first off, folks, welcome back. I've got some reminders for deadlines up here. Today is the deadline for homework one, so please try to get as much of that finished as you can. You do have a 1 point late penalty if you're not finished with it. It's just 1 point across the board. It's not per day or anything like that. As a reminder, you all have 3 extra credit points already from having done homework 0 to test the system. So you've got some room to maneuver if things are not shaping up the way that you'd like. If you need any help finishing that, or if you're still fighting with SAS or Stata, please let me know, and I'm happy to help troubleshoot with you guys. The other thing that you can be working on is your second formative assessment, which is due on Monday night. That way we can go over it on Tuesday. So that's available inside quizzes and icon. Just as a reminder, it's not graded. I look to see that you put forth an effort, and the idea is just to write a couple sentences for each question as a way to structure the review of the material in between assignments. So those are things we can be working on. Just a little bit ago, I put up some new material for the end of next week, Lecture 3 and Example 3, and I will let you know when Homework 3 that goes with it is available. Homework 2 is available right now that goes with the Example 2 we're going through, and you are able to do some of that if you want to work ahead. If you say to yourself, I just don't have enough things to do and I need to find something else. Or perhaps if you are avoiding something else, like writing something that you don't want to write, statistics homework is an excellent way to avoid doing that and yet still be productive, right? So, might I recommend my class as a procrastination opportunity for other things? All right, so any questions, comments, logistical things we need to talk about? No, we're good? Okay, what did we talk about last time? As usual, I will accept letters, words, gestures, anything that comes to mind. Eagerly awaiting the chat window. Fisher. Yes, yet another old white guy to go along with Pearson in our collection so far. Transformations. Yes, we reviewed linear and nonlinear transformations, such as z-scoring is a linear transformation that will show up in the context of correlation. We reviewed standard deviation versus standard error again. So talking about differences between people within a sample is what the standard deviation characterizes. Differences between samples in, say, the sample mean or the sample correlation or some other sample statistic. That's what standard error is meant to convey. Very good. What else? Correlations. Yes, Pearson's R. Yes, so correlation is a general term. There are lots and lots of kinds. Pearson's is one specific kind. All correlations, though, share the same metric. They range from -1 to +1, where 0 means no relationship and 1 means a perfect relationship. If it's positive, then as x goes up, y goes up. If it's negative, as x goes up, y goes down. So negative means the two go in opposition of each other, and you'll get a chance to practice that on homework too. Let's see what else we got. Compute standard errors require new different ways and a confidence interval for R. Yes. So R doesn't come with a ready-made standard error with which to make a confidence interval because R is bounded. So that's where I think we left off last time, and we'll get a chance to see how to make Stata and SAS give you confidence intervals for bounded statistics such as R. Question or comment, the program has an example results section, which is great because it does the work for your dissertation. Yes, the example 2, is that what you mean? There you are, Mary. I'm looking for Mariana. Yes, there you are. Yes. See, the secret about technical writing is that it is highly formulaic. The more boring it is, the easier it is to understand. And it's so formulaic that I can literally have the computer do it. And so as we get further into this class, in addition to the drop-down questions for about multiple choice answers for things, I'll have you be completing results sections in this formulaic pattern. And my hope is that between the homework assignments having those templates for you, as well as having the result sections with the examples, that you'll have a list of things that you can copy and paste into your dissertation. And with some careful find and replacing, you'll have a structure used to be able to help you learn how to do result sections. So yeah, that was the goal. So I hope it is helpful to you. All right, so those are good review things. I think that's the main stuff that we talked about. Anything else on the list before we jump back in? Okay, then let's get out of the web page here and pick up. Let's go to the, well, that's where we left off, I think. So this is example 2, picking up on page 4. So just as a reminder, from this point forward, each lecture that goes over general concepts is going to have a corresponding example where you have the actual code and output from the programs that's built into the lecture. And so you can actually see where the numbers that were in the lecture came from for particular example analyses. The example 2 data that goes with this. It's the same file that went with example 1. Those are also available for download separately so that when you do your homework, you can refer to those syntax files as templates that you can copy and then move over to your homework and figure out how to write the code from those. So just as an FYI, you don't have to retype all this stuff if you don't want to. For some folks, that's helpful to have to do it, so that's fine too. Question?
Yeah, can I ask you a question? I tried to look for what you have right now, but when I went into like the class number and example 2, it opens through like Stata, so it doesn't let me see it like you can see it and you can write notes on it.
So this handout should be a PDF format. Let me show you what that is. Back to the web page here. So this handout that I am looking at right now, it was posted on 9/17 as example 2, and the files that built it are inside the zip folder. And so
Okay,
inside the zip
my bad.
folder
Thank
is
you.
the zip folder has the files that end in .do for SAS and .sas, or .do for stata, .sas for SAS. And those are the syntax files that basically the snippets that I pulled from to build the example with. So you can take notes in the syntax files if that's easier, or you can follow the handout. The reason that I like to do the handouts is because then you can put the syntax and output next to each other, and it's sort of like cause and effect in terms of how to get the program to give you the information that you're trying to ask for. Okay. Other questions on where to find stuff or otherwise? Okay, cool. All right, so then this is where we were looking at our first instances of Pearson correlations. So just to review, Pearson correlation is a measure of association that is appropriate for associations between quantitative variables or binary variables. We haven't talked about the binary part yet, but you can do this for binary variables as well. The variables in this example are continuous. One of them is income, which somehow lost its I there, and education. So income in thousands of dollars and education in years as the two quantitative variables. We had 3 different versions of income here, just for me to be able to remind you what linear versus nonlinear transformations do. So the second entry in this table, income Z, is a linear transformation of income that has shifted the mean to be 0 and the standard deviation to be 1. That is known as a z-score transformation specifically, and that tends to be used whenever you have multiple variables that are on different scales and you want to be able to somehow compare them or compare their association strengths. That's more in the context of models, but the idea of a z-scored variable shows up in a lot of places. And so what this table is reminding you, this number right here, for instance, that's a correlation of 1 between original income in dollars and the z-transformed version, because a linear transformation does not change the information that's in a variable. It changes all the values to an even extent. It just changes the scale. In contrast, this correlation right here is with income in dollars with log transformed income in dollars. That's a nonlinear transformation, And a log transformation in particular is used to take positively skewed distributions, this way for you guys, and reel in the extreme values. And it also takes the other side and stretches it out a bit. So if one were, for instance, concerned about people in the sample who made a lot of money somehow skewing the results for how income is related to other things, this type of transformation could be a way to reduce the impact of that potential additional skewness or those extreme values. Down at the bottom here is an example of a correlation between income and education. Correlation is 0.38. So that's positive, right? We know what that means if it's a positive correlation, as x goes up, y goes up. But it's not a lockstep relationship because it's not a correlation of 1. So it's not a guarantee, so to speak. It's a medium-sized relationship. There are conventional standards for what is considered small, medium, and large, but they're largely outdated, and so I don't want to teach them to you. It's a correlation of 0.39 or 38. That's what it is. I don't think it helps anything to say whether you consider that small, medium, or large because it depends on your discipline and what people tend to expect. The thing underneath that, this less than 0.001 thing, what's that? P-value. Yes. P stands for what? I'll give you a hint. It's not urine. Badoom. Thank you. I'm here all week. Uh, alpha, it's related to alpha. Yes, P stands for probability. It's the probability of getting the result as extreme as you did if the null hypothesis is true. And P is related to alpha. Alpha is the a priori p-value that you set as your cut point for what is going to be considered too unexpected and thus significant. So traditionally we set an alpha of 0.05, meaning that if the null hypothesis were true, then any result that would happen less than 5% of the time under that distribution would be deemed unexpected. So we would judge this table with an eye towards that a priori cutoff. Anything less than 0.05 is declared significant. If you wanted to be more conservative, for instance, if you know that you're going to be looking at a bunch of correlations, an alpha of 0.05 means that any 1 out of 20 could be significant by chance because you're saying 5%, not no percent. So if you want to be more conservative, you might set an alpha to be, say, 0.01 to have a stricter cutoff for what you're willing to say is unexpected or significance, because an alpha of 0.01 means that only one time in 100 you would expect to see a result that extreme just from normal sample fluctuation. So alpha is the ahead of time decision that we compare these obtained p-values to. Alpha will also be known as type 1 error rate very shortly, for those of you who've seen this stuff before. It's coming. I just haven't got there yet. So in this table, unsurprisingly, and I say unsurprising because of this right here. Make sure you can all see that. What have I highlighted? What does n equal 734 tell me? Sample size, yeah. And so unsurprisingly, because I have 734 people, it doesn't take much to declare a correlation unexpected if the null hypothesis of zero correlation were true. We have a lot of what is going to be known as statistical power. We have a good chance of finding effects that are small at this sample size. So everything on this page happens to be significant at a p less than 0.05. The difference across them lies in effect sizes. Correlation, say, of 0.8 is a much stronger effect than a correlation of 0.38, even though they're both equally significant because they have crossed over that threshold of happening less than 5% of the time. Okay. And this thing up here reminds you what the p-values mean in engineer language. The probability of an R that's either positive or negative under the null hypothesis that the population correlation is 0. That's what that's telling. It's trying to tell you what this p-value means under each of these things. Okay, questions on any of that? No? All right. Then the other part, confidence intervals. As part of my proc core command in SAS, I have asked for the Fisher R to Z transformation. This is a nonlinear transformation that converts an R correlation, which is bounded between -1 and 1, into a Z metric that is unbounded. It ranges from negative to positive infinity. So where this table comes from, I have put below here. Step 1 is to take the sample correlation. So right here, for instance, let's grab this one. This is the correlation between income and education. It's 0.38. To be able to get a sense of that correlation's wiggliness across samples, its expected variability given our sample size, we first need to convert it to a z, which, hang on, come back here, is the next column over. And that column is the result of this formula. So we see our friend natural log in here. It does the same thing. It takes the boundaries and sort of stretches them out on both sides. Here's a mapping of R on the x-axis to that z value on the y-axis. And so you can see the stretching happen as the yellow line that sort of heads off as R gets closer and closer to its boundaries. The next column over is the bias adjustment, which is the difference between the R as computed the regular way and the R that is adjusted for sample size. Given that we have a large sample size here, these adjustments are very small. So then we have the adjusted version of the correlation and then the confidence limits around it, which come from the last step here. So we compute the standard error on the z-score, the limits of the confidence interval on the z-score scale, and then we back translate into R. So when all is said and done, you get this thing at the end here that gives you the range around your correlation value for this sample. So what is this supposed to tell you? It's supposed to tell you the range in which, across repeated samples, the population estimate of the correlation would be found 95% of the time. I personally don't like that definition, but that's what it is. So you can just think of this as a way of conveying to your audience how imprecise your correlation estimate is. In this case, it looks like it's anywhere from 0.32 to 0.44. It's a fairly narrow window around it because of the large sample size. The larger your sample size, the narrower the confidence interval is going to be around any one sample's estimate. So you will see in the results section for this example that I reported these confidence intervals in addition to just the R itself as a way of explaining to the reader sort of the level of precision that I have in estimating this relationship. Okay, I think that was all I wanted to say about that. And here's a picture. So, how imprecise what is the question? How imprecise the correlation estimate is. Like, is it 0.38? Yes, or 0.38? Like, the more people you have, the more faith you can have. It goes back to the idea of a sampling distribution for the correlation. Let me pull that up 1 second. So I'm switching back to the lecture for just a moment. This is lecture 2, slide 2. So this is a picture of sampling distributions. So I simulated data where I knew what the right answer is for the population. I have 100,000 fake people. And I simulated two variables that either had a true correlation in the population of 0 or zero point 0.8. And the first row of this table on slide 20 shows what it would look like across different samples of the same size for a true population correlation of 0. So if I take 10 people from this 100,000 people fake data set, I create a sample of 10 people, I compute a correlation, grab another sample of 10, compute a correlation, and I would do that 1,000 times, I made this picture from that. If I do it 50 times, I got this picture, and if I do it 90 times, I got this picture. So what this is showing is that any one sample is not going to be the right answer, right? We know what the right answer is. It's supposed to be 0, but when you only have 10 people, it really matters which 10 you grab out of that population. The correlation that was obtained from those 10 people ranges almost the entire possible values. It ranges almost the whole way from -1 to 1, even though I know the right answer is 10. So when I say imprecision, I mean this idea. The idea that if you redid your study, would you get the same answer? And if not, how far off are you likely to be? The fewer people you have, the more off you're likely to be, the more imprecise any one estimate from one sample is going to be. And so part of your due diligence in conveying your results is accurately characterizing the expected inconsistency. And a way to do that is through standard errors or confidence intervals or both. Okay, question. Do you have your hand up?
Yeah.
Okay, hit me.
I don't know how exactly to phrase this, but say you have 10 samples with 10 participants each, and then in another experiment with all the same parameters, you have say 2 samples with 50 people in it each. So there's the same number of participants overall, would they still have the same statistical power behind them?
No.
Okay.
It doesn't matter how many samples you have, it matters how many's in a sample.
Okay. Okay. Gotcha.
Yeah, so each of these pictures was made with 1,000 replications, but that was mainly just to make sure that the image of the mound is all the way filled in. Like if I had only done this 10 times, it would look noisier, but the same premise would be true. What any one sample's correlation estimate is going to be is way more variable when you have fewer people.
Okay. Yeah, that explains it. Thank you.
Okay, good. Other questions. So does that mean imprecise measures test-retest reliability? Um, I I wouldn't say it measures it. I would say it is related to it. So test-retest reliability is the idea that if you gave, say, 2 variables to a sample and you have a correlation estimate, you have a score for each person, and then if you gave them the same variables again, then how related are their scores? Um, that has to do more with the precision of the measure itself, but you would generally expect that a better test-retest correlation in terms of a better version of it would be obtained with more people. So let me put it another way. If you have a measure that's super reliable, so like my Fitbit here, I'm actually transitioning into the second class after this here. I think that my Fitbit is very reliable, but it is not necessarily valid. Reliability versus validity, right? Reliability is the precision with which you measure something. Validity is whether or not you've measured the right thing. So every day my Fitbit has whatever algorithm it uses to decide how many calories I'm burning, how much I've moved. If I'm teaching, I get credit for more steps because it thinks I'm walking around right now. So I can just like sit on my couch and do this, right? And that counts as my activity for the day. It's reliable, but it may not be valid. Um, so if you have a measure like a Fitbit that's algorithmic and it's super reliable, you should get a strong test-retest relationship, right? If I have how many steps I've taken today versus how many steps I've taken a week from now, like that should be a really strong relationship. but my chances of finding the relationship that's correct, like the real one in the population, is stronger if I have a higher sample size. Like it's just results are more believable is what it comes down to with more people. It's more likely that you could just get like one rando in your sample that skews everything like the wrong way when you have fewer people. There's my technical definition. We're going to go with rando for today. When you have a sample of 10 people, one rando can screw it up more than if you have a sample of 90 people. So if you had a low test-retest reliability, it could be because your measures are not that reliable. Think about like an old school step counter. Have you ever seen, you guys are old enough to know what that is, right? It's the other class that are a bunch of children that weren't alive in like the 80s and I have a hard time relating to. Like the step counters that you used to clip to your belt, like those are much less reliable. If I wanted to talk test-retest reliability of a step counter clipped to my belt, right, it could be that that's just a bad instrument, or it could be that I don't have enough people to get a stable estimate of the test-retest reliability. So I'm kind of off track here, but I'm trying to answer questions. Does that help? Maybe? Okay. Yeah. And thanks to you guys, I burn an extra 200 to 300 calories on days I'm teaching. Did you know that? I do. Either it's because my resting heart rate has climbed above "is she awake?" or because I'm doing all this walking right now. So, and yes, I have a desk that is capable of standing because my husband picked it out, but I am never going to have a standing desk. Do you know why? Because the reason that I got a PhD is to earn the right to sit the hell down when I work. I had way too many crappy jobs where I was on my feet all day, right, wearing a name tag. I was a waitress. I worked in a bagel shop. I worked at Walmart tucking shoelaces back into shoes for $4 an hour. I did that. I am sitting down. I have earned the right to sit down. That's my philosophy. So yes, maybe it would be more calories if I stood up for class, but I'm unwilling to do that. Ironically, when I'm teaching in person, I am standing up because I'm usually behind some sort of desk or podium, but that's the exception to the rule. So anyway, I'm off topic, but okay, more people makes things better. How's that? Is that a good summary? More people, more belief. So in conveying your results, conveying some estimate of how much you believe it in terms of confidence intervals, standard errors, and things like that is essential. All right. Okay, I think that's actually a good place to transition back to this. Let me check to make sure. Oh yeah, I have pictures. By the way, in all of the examples, I'm going to have pictures of stuff and code that makes pictures. You guys don't have to do pictures for your homework. So I probably won't focus on that code very much because I'm not expecting you to do anything with it. But because making pictures is so important, I wanted you to have examples of how to make pictures. So for instance, this is a scatter plot that has a line through it that shows the correlation between education and log transformed income. Top one here is a scatter plot that shows the nonlinear relationship between original income and income that has been log transformed. And so you can see the stretchiness of the original variable on the x-axis gets way condensed on the y-axis, relatively speaking. And that's actually a very nice segue for what's coming next, what Pearson correlation doesn't tell you. All right. So Pearson correlation has a very particular kind of association that it captures. And that association is linear. It's not a coincidence that when people show these pictures to illustrate Pearson correlation, there's always a line drawn through some dots because that's what it's measuring. So I'm picking up here on slide 22 of lecture 2. So for example, earlier in this example, we had 10 hypothetical men measured in height and weight, and I found a correlation of 0.99. Here's a picture that goes with that data. So you can see a very strong line fit through this versus another two variables that I made up, and I made them up to have no correlation. But in the sample that I created, I actually had a slight negative correlation, but you can see it's a lot weaker. Um, Pearson correlation is not enough, though, to describe associations between quantitative variables that don't take this linear form. So for instance, this shape right here, this scatter plot shows a classic U shape, where if you have a little bit of something, then basically more is not better, up to a point then more is better. So for instance, a classic relationship between arousal and performance, right? That's a U-shaped relationship. Like if you don't give a shit, that's not good. But if you are so anxious that you can't breathe, also not good. And the right amount is somewhere in the middle. There's a lot of things like that where more is not always better. More could actually be worse, or there's some point at which more doesn't help. And those kinds of relationships are not going to be picked up accurately by Pearson's correlation. If I try to draw one line through this whole plot, it's not going to work. It actually says that there's no relationship here, even though there clearly is. Here is a classic set of data, Anscombe's quartet. All four of these pictures show the same correlation of 0.82. But clearly there's different things happening in each. The only one that's really appropriate is the top left here, where you have a linear relationship, and that is indeed what it looks like the picture has. There's a nonlinear relationship in the top right that's not being captured. The bottom here shows that this would be a perfect correlation, except for, again, one rando messing things up in a sample of 10. And the bottom right here shows that there would be no correlation at all, except for one rando who's pulling the line. So randos are bad. Randos will be called outliers shortly. That's the technical term. I wouldn't recommend putting rando in your professional writing, but we can talk about it that way in class. So what do you do instead? Well, you come back for the rest of the semester, because that's one of the next things that I have to teach you is to how to describe associations between variables that take other forms, nonlinear relationships among quantitative variables as one example. So we will get there. Pearson's correlation is not the only game in town. Pearson's correlation has some synonyms that you should be aware of. This is an example of people relabeling things for no reason. So if you compute a Pearson's correlation between two binary variables, someone else may call that a phi correlation. That's the same damn thing. If you compute a Pearson correlation between a binary variable and a quantitative variable, that is called point biserial, and that is the same damn thing too. The different names come about because there are computational shortcuts to the Pearson correlation formula that binary data affords you. But if you have a correlation whose input requires means, variances, and covariances, it's a Pearson correlation. So just so you know that, there's really only one kind. There is a different correlation, though, that I do want you to become acquainted with, and it is yet another dead white guy, Spearman. He has a correlation that people will sometimes report, and it is known as a rank order correlation. The trick to this is first you take the two variables that you want to look at an association for, and instead of using their original values, you compute them to the rank order. So the highest score is number 1, the next highest is number 2, and so forth. Then you fit a Pearson correlation to those rank orders instead. And the end result of that process is known as a Spearman's correlation, which, just to be mean to you, is called rho, even though population correlation was called rho 10 minutes ago. I'm sorry, it is the way it is. I just write out the word rho when I write things because I don't trust that my readers are going to know what this P looking thing is in most journals that aren't like quantitative journals, but that's what it is. It's the Greek letter. I did hear that we're up to what, beta for tornado or hurricanes now. So you'll get a chance to meet the Greek alphabet if you watch the Weather Channel. My son is learning his Greek letters now by doing so. He knows alpha and beta so far. I think chi might be next. whatever C is, delta, epsilon. Yeah, I know quite a few of them, but not all of them. So I'm looking forward to getting to know the rest of the letters. Spearman's correlation is used for two purposes. One is for ordinal data, so really where rank order is the only thing that you can trust in terms of numbers being numbers, and the other is to diminish the effect of extreme values. So for example, if you have data that look like this on the left here, the Pearson correlation and the Spearman correlation would be about the same. There's nothing that really changes from going from the original values of the variables to their rank orders. In contrast, something like this in the middle, this would be a Pearson correlation of only 0.88 because of these tails here. But if you don't go down as far as y and you just think of it as like the next one, the next one, the next one, then that translates into a Spearman correlation of 1. Likewise, the opposite happens here. I guess that's the same pattern, just a different magnitude. A Pearson correlation on this right panel here would be 0.67 because these guys are so far away. If you reeled them back in to be just like the next cases, that would result in a higher Spearman correlation. So this is something that you will occasionally see, so I wanted you to see it. And the good news is that it is also available in SAS Proc Core and in the state of command known as Spearman. So let's look at that before we jump on. So back
I
to
actually
the
have a
handout.
question.
Please, let me get this pulled up
Um,
and get your question.
so when we're trying to figure out if there's a correlation between two variables and we don't necessarily know what form it might take linear, it might be nonlinear, whatever. Would you recommend like running the Spearman? I'm blanking on the name. The Spearman
Correlation?
correlate. Thank you. A row. Yes.
Yeah,
Okay. The Spearman row first, like to get a sense of that, or would you recommend like plotting it and taking a look and being like, oh, this looks like a U shape. I should look at different things. Like, what's kind of your step for looking at correlations, I guess?
I do think pictures are helpful, but if you have a ton of data, it's really hard to see a pattern. It just looks like a big blob at that point. The thing about Spearman is that it doesn't tell you what kind of functional relationship you have. Because if it is nonlinear, like you need to know which kind of nonlinear. I would put it into a model, to be honest. Like the Pearson correlation and the Spearman correlation will give you some indication that there is a relationship, but to refine that, it needs to go into a model. So just as foreshadowing, right? I have education and income related here as if one more year of education means the same thing at all points in the scale. But we know it doesn't, right? There's something magical that happens when you hit one more year that yields a degree as opposed to just one more year that doesn't yield a degree. So that implies that this sort of linear relationship is insufficient in describing these. And so I would have to use my knowledge of what education means, thinking, okay, well, there's probably a sort of a stopping point at 12 years of education, maybe another one at 16 or 17, and then maybe another one that would correspond to graduate level, and think about how to incorporate those stopping points, so to speak, into my function. If it was some other context, I would have to use my theoretical knowledge of that context to try and guide what type of shape would be appropriate. Is it a more isn't always better? Because that would be like an asymptotic kind of thing where the line kind of levels off. That would correspond to an exponential or a log function. Versus a U shape where more is good up to a point and then more is worse, that would correspond to a quadratic. So I don't think there's an answer that works for every situation. It has to be some kind of blend of your content knowledge about the variables you've measured and how they should behave, what other people have found, and then trying to incorporate that into a modeling process that pays attention to those nuances.
Great, thank you.
Sure. Yeah, it's not a ready-made answer, but there are a few. I don't think there's anything that would be wrong with running quick correlations because it would be unlikely that whatever relationship you would find would be completely obliterated by the line. right? Like a perfect U is very rare. There's usually like a U-ish after some point. So these sorts of things can still be used descriptively to yield that. Just realized I forgot to do the Stata part. So Stata people, you got to remind me when I forget you, okay? I'm sorry. I didn't mean to do that, but the Stata output looks exactly like the SAS output with one exception. It also puts the sample size inside the table after the p-values. And this is something about Stata that drives me nuts. Rather than reporting the p-values as less than 0.0001, it says they're 0, but they're never 0. You can't have a 0 probability. So what they mean is it's 0 to 4 decimal places, so less than 0.001. PW core is the command that you would use to get, it stands for pairwise correlations that builds this matrix. There is also a just regular core command. Do not use that one. I learned this last year. The regular core command does what's known as listwise deletion. What that means is that if you give it a series of variables that you want correlations among, it will only estimate the correlation on somebody who has all the variables. So it cuts your sample down relative to what you actually have, and that's often not helpful. So don't use that one, use this one, which uses all the people that you have. So if you had missing data in your sample for some of your variables, you would know that because the sample size that's given for each pair would be smaller for some pairs than others. And the same thing would be true in SAS, by the way. If you have missing data, it will print the sample size inside the table so that it corresponds to each pair of relationships.
I'm sorry, can you elaborate on that piece again? So with the pairwise piece, because it's, if somebody's missing a value for something we're trying to correlate, we wouldn't want them in the model because they're missing a data point, right? But the list-wise is if we're looking at a bunch of variables?
Yes.
Is that, okay, got it, thank you.
Yeah, listwise deletion means that like if I have 3 out of the 4 variables that I could contribute correlations to, I still get kicked out of that. I don't get to contribute anything.
Got it, thank you.
Yeah, so listwise deletion is bad news. We don't want to kick out data unless we absolutely have to. And what to do instead? Take my other courses. I'll be happy to tell you. We just won't get to that this one semester. Other things in Stata, they have a confidence interval for correlations. It's not something that came with a root Stata, but one of the nice things about Stata is that programmers can contribute their own packages, similar to what happens in R. And so I asked the Google, how do I do a Fisher R to Z transformation in Stata? And it told me to go find this routine CI2. So this command right here, ssc install, means you type that into your window and it goes and finds the package and installs it into your local Stata. And you can do this on the virtual desktop. You do have that level of administrative capability within your installation of Stata to be able to do that. And those of you who've bought Stata can do it as well. And so then once that's installed, I'm able to run CI2 and it only does one pair of variables at a time. So then I have, I just demonstrated one of them, and you get this handy dandy text that spits out that tells you that the correlation was 0.305, for instance, with a confidence interval of 0.238 to 0.369 around it. So it gives you the only difference between what it does with respect to SAS is that this is not the sample size adjusted correlation, it is the original. In SAS, you can choose whether it's the sample size adjusted version or the original. So just be aware of that. And here's some words, as I pointed out before. My gift to you, words. All right, so Spearman. Let's play Where's Waldo? What's different about this proc core that gives you a Spearman correlation rather than a Pearson? Don't think too hard. Make it a little bigger. This guy right here, the word Spearman as an option. Yep. So it actually will give you both because Pearson is a default, and then Spearman right here is an add-on. And when you do ask for Spearman, it also gives you the median as one of the simple statistics. So I wanted to point out the characteristics of the variables that I'm using in this example. Income is one of them. The other two variables that I'm going to be correlating with income are ordinal measures. So one is how often you socialize with friends on a 1 to 7 scale, and the other is how happy you would consider yourself to be, which is on a 5-point scale. So if I look at these medians here, what does that tell me about the likely distribution of these variables? For instance, a median of 4 for how happy you think you are. The range is 1 to 5, so what does a median of 4 tell me about this distribution? Pretty happy, yeah. In stats terms, yeah, positively, or actually it would be the other way. It's skewed. Which way does the tail go? Yeah, negative, because most of the people are on the high side, right? So this is an example where there's a big chunk of people sitting at 4 and 5, and there's not as many people who are willing to say that they're unhappy. A median of 4 on a 7-point scale suggests something that looks a little bit more symmetric, right? The middle value is 4 on a scale of 1 to 7. So given that these are ordinal variables, I'm going to look at the Spearman correlations of those. And here we see results that are actually different than last time. Not everything is wildly significant. So here's the first one. This is the Spearman correlation between income and how often you socialize with your friends, where higher values mean more often. So what they've done for income is converted into a new variable in which whoever made the most money, whoever made the least money is given a rank of 1, and then the next income is 2, and then the next one is 3. And different software handle ties in different ways, but just the idea that this is a rank ordered version of income rather than the original dollars. What does that Spearman correlation tell me? The value here between income and time spent with friends is negative 0.05-ish. What do I conclude about the association between these variables? What do you think? See, this is the audience participation portion of the program. I can see some of you talking to yourselves. Not significant. So this number right here doesn't tell me about, but the one underneath it does. So I'll give you that. Very small negative association, very weak negative association. Yes, I will take either of those. So it's very close to 0, and it's on the negative side, which means just a little bit. If I spend more time with friends, I am likely to make more money or less money. Less, yeah. Or put the other way, if I make more money, I am likely to spend a little bit less time with friends. So relative to my null hypothesis, what's my null hypothesis here? What's my benchmark? Anchor point. No relation, yeah. Correlation is 0. So relative to that, how often would I find a correlation that is larger than 0.05? The p-value underneath it tells me like 21% of the time. Yeah. So is this expected or unexpected? One vote for expected? We'll take a vote. Expected? Okay, any votes for unexpected? A lot of abstains, it looks like. Yes, expected, meaning if the true population correlation were 0, would normal sample fluctuation be likely to give me this result? Is this within typical fluctuation territory? Yes, it is, because that's 95% of the time, and unexpected territory is 5% of the time. So because this p-value of 0.21 is greater than 0.05, that means we're within expected territory. It is not a significant association. And we reject or do not reject the null hypothesis then. Which one is it? Do not reject, which I would say is retain, but not accept. So yeah, we do not have evidence that we have a correlation worth paying attention to. It's within expected territory, and it's numerically very small. Same story to some extent here in terms of the magnitude. So does money lead to happiness? How's that for causality? Yeah, correlation of 0.05. It's a positive correlation, so mo money, mo happy, but it's a non-significant correlation. So it's a tiny relationship, very close to 0. P-value says that a relationship this large or larger would be found around 18% of the time if there was really no relationship in the population. So this is well within expected, do not reject, non-significant. All those words go together. Another way to think about this is that if I were to build a confidence interval around that correlation, that confidence interval would include 0. So it includes the expected number. That means we're within expected territory. If the confidence interval does not include the expected number, then we're in unexpected significant territory. Homework question. And then last but not least, friends and happiness. Does having more friends make you happier? Couple votes for yes. Or does being happier make you have people want to be your friend more? Yes. Can I distinguish between those two possibilities for mechanisms based on these data? Absolutely not. No. You can call one of them Y and you can call one of them X, but there's no way to say anything about that. Yeah, these are positively related. That's what it means. We can attribute it, without design, we cannot attribute causality. Absolutely. So is this a significantly positive relationship? Do I have something to talk about in my results section? Yep, what am I looking at that tells me that answer? That one right here. So in your homework too, I'm going to ask you several times. You'll have drop-down choices that say things like significantly positive, non-significantly positive, significantly negative, or non-significantly negative. The direction of the correlation tells you the positive versus negative, but the significant part comes from the p-value. That p-value is less than the alpha level, so we set alpha at 0.05. This p-value is 0.02-ish, so less than 2% of the time we would find a correlation that big if the null hypothesis of no association were true. Therefore, this is in unexpected territory. It's a significant positive correlation. Okay. Now, do I get super excited about this positive correlation? Am I going to go submit this to Nature or Science or someplace like that and make a big deal of it? No. Maybe People Magazine or Psychology Today, something like that. Well, do you think Psychology Today would get excited about a correlation that's 0.08 in magnitude? Yeah, so this is a good example of just because something is significant doesn't mean it's a strong effect. This is a positive correlation, but it's just barely above zero, right? These things are just over the needle in terms of being related to each other. So it's certainly not a lockstep, more friends makes you happier or more happier makes you more likable, any of that stuff. So both of those things would need to be acknowledged. It is significant, but it's a small effect relative to the largest effect. What's the largest it could be? This is a hand signal one. You can all do it. What's the largest it could be? Yeah, 1. We are number 1. Indeed. And
Lisa,
just, yeah, and you got confidence intervals around the Spearman correlations as well. Question?
I have a question. Does it matter when talking about this sort of thing that these are ordinal scales, or
It does matter, and that's why we're looking at Spearman correlations as opposed to Pearson correlations.
I see. Okay.
Yep. There are other kinds of correlations that are designed for ordinal scales as well, but those are not something that we'll have a chance to get into. They are known as polychoric correlations, specifically for ordinal scales. And they are also designed to deal with range restriction problems that show up from only having so many values to correlate, like 1 to 5 scale or a 1 to 7 scale. All right. And here's some words to talk about all of that. And Stata folks, I didn't forget you. To get the median, there's another thing I downloaded called Univar. That's one other way that you can get the median. It generated this nice little table. Same thing that Summarize will give you, but Summarize has more information in it. And then the magic word to get a Spearman correlation is Spearman. You list the variable names that you want the correlation for, comma, sets off a request for an option, and then there's an option called stats in which you can ask for the correlation estimate itself. OBS is Stata's version of n for sample size, and p gives you the p-values. So to make this table look like the one that was generated for Pearson correlations, I added all 3 of those options. And it gives me the sample size, but that otherwise gives me the p-values and the correlation estimates the same as from SAS. And then here's an example of the Fisher-Z transformation to get the confidence intervals. So for instance, this confidence interval around here goes from minus 0.118 to 0.027. So because the confidence interval includes 0, that's another way of saying the result is not significantly different than it's not significant. It's not 0 is within the possible range. Okay, what's next? I think we're on to a different topic. Yeah, different topic. Okay, how we doing, folks? Yes, getting there? All right. So we talked about quantitative variables. One more thing to tell you about with respect to that before we change gears, in the context of reliability. So this is something that you will have to demonstrate a lot of times when you're doing coding systems, for instance. Do any of you work with data where you're observing behaviors, like counts of things that happen or ways that people interact with each other, any of that kind of behavior? Yeah, that's fairly common, I've learned. And one of the things that you'll have to demonstrate is that 2 people who are viewing, say, the same recording or watching the same observation would come to the same conclusion about what they're saying. And so you'll have to demonstrate what's known as inter-rater reliability for those sorts of observational measures. A lot of people will unknowingly decide that the measure of inter-rater reliability that they're going to use is Pearson correlation. Don't do that. Pearson correlation throws away differences in means and standard deviations across raters. So it only measures relative agreement. It cannot measure absolute agreement. So if you want to be able to gauge the absolute level of agreement, like if Rater 1 gives this person a 5, does Rater 2 give this person a 5? Like we need to be able to have faith in the scores per se that are being given. That's a job for our friend Intraclass correlation. So it's ICC for short. Intraclass correlation shows up in many different contexts across statistics. In this context, it's a way to look at agreement across raters for quantitative variables. And the formula for it looks a lot like the formula for Pearson correlation, with one main difference. Rather than for each variable, when you're trying to compute the covariance, using each variable's mean separately. So in the formula for Pearson correlation, like this was X bar and this was Y bar, it uses the same mean for both. So the deviating part of the formula is deviating all the scores around a common mean, rather than having a mean for rater 1 and a separate mean for rater 2. So absolute magnitudes of the ratings and discrepancies therein get carried through. And the same thing is true with the variance. You compute a common variance across all of the observations. And so the variability that occurs between raters is maintained as part of this formula, and it actually counts against you as your index of agreement. So you will see this show up in other contexts of statistics when you're dealing with sampling across multiple dimensions. For instance, if you have multiple children sampled from multiple classrooms, intraclass correlations will be used to describe how much of the variability in the data is due to which classroom a child is in versus which kid it is. This formula can also be extended to more than 2 raters, whereas Pearson does not. And it also can be extended into what in measurement is known as generalizability theory, which is all about trying to quantify and distinguish sources of variability that occur for different reasons. So for instance, if you have a coding project where you're watching multiple subjects over multiple occasions and there's multiple raters doing the coding, even if not every rater sees every subject every time, if you have enough overlap, you can still look at interclass correlations to try and distinguish how much of the variability is due to which subject it is, which is the one you care about, versus which occasion it is, versus which rater it is, versus some interaction of the two. So ICCs show up a lot in statistics. Just put a pin in this, like in your head, like put inter-rater reliability equals interclass correlation. I won't have you do this for this class, but I wanted to put it out there as so that you're aware that that's what tends to be done, or should be done, I should say. So pictures, just to show you differences in what it would look like. For the picture on the left, the means are very close and the standard deviations are the same. And so in this case, a Pearson correlation and an intraclass correlation would converge onto about the same same number. Whereas on the right, the rater on the right side here, test 6 as I'm calling it, has a mean that's a lot higher. And so the fact that that rater is consistently higher than the other one would translate into an interclass correlation that is lower than what the Pearson correlation would translate into. So absolute differences in agreement would count against you, which is important if that's what you're trying to track reliability for. So have any of you seen this before? Interclass correlation? No, I hadn't either. So this was brand new to me, but just know that if you're in a situation where you're trying to do reliability across a lot of things, like this is the framework that will be most useful to you. And I have examples that I can send you readily if you're in a situation in which you need to do this.
I have a question.
Sure.
I have familiarity with Cohen's kappa.
Mm-hmm.
So how does that compare to this?
Cohen's kappa is for categorical variables.
Got it. Thank you.
And it also adjusts for base rates of expected agreement based on differences of the frequency with which each of the decision types are made.
Thank you.
Yeah, but that is another measure of inter-rater reliability just for different types of variables. Okay. So the thing about correlations for binary variables, this is another seed that I want to plant for you. Pearson correlations for binary variables are going to be limited by the proportion of people in each category. More question. So you can compute Pearson correlations between binary variables. That is just fine to do. However, the maximum relationship that two binary variables can show is going to be limited anytime that their means are different than 50-50. So here's a chart that shows you the effect of range restriction. For instance, if I have a variable x that has a mean of 0.1, so if these are 0, 1 variables, a mean of 0.1 means that 10% of the people in my sample got a 1 and 90% got a 0. And if I try to correlate that variable with another one in which 20% got a 1 and 80% got a 0, even if those two variables are perfectly associated, the strongest Pearson correlation that can give me is 0.67. So binary variables tend to have smaller associations between them, and that stands to reason because there's less information, right? That is practically a constant in the case where you only have 10% of the people who don't have, that have a different score. And it gets really hard to show associations with constants. So while it is valid to look at a Pearson correlation among binary items, it's not necessarily the best strategy. It's going to be an underestimate of the true association. And so there are all these other correlations that we're not going to have a chance to talk about that I just wanted to give you the words because you may see this. Yeah, these are big words. That was a nice. Pam's like, what? Yes, if you want to sound smart, you can learn how to pronounce these words. So for instance, in the class that follows this one, which is about factor analysis and structural equation models, in a few weeks I'm going to be talking to them about tetrachoric correlations. There's a mouthful, which is for binary data, and it's trying to come up with the correlation among the continuous underlying variables that created the binary responses. It kind of sounds like voodoo, but there's actually a mathematical basis for it. The same idea if you have ordinal variables, a polychoric correlation is designed to provide a more, say, robust, higher, in most cases, more accurate representation of a relationship between ordinal variables that tries to take into account the limiting effects of range restriction. So these words, if you see any of these words, these are not Pearson correlations. These are things that you cannot solve by hand. Like you could not open up Excel and find this stuff. These are things that have to be found through iterative algorithms using maximum likelihood estimation or something along those lines. So just know that further in statistics, people have found ways to deal with this problem. So if you're in a situation where you're trying to describe associations between, say, binary variables, these are options that you can use within SAS and Stata to get these things for you instead, and that would probably give you a better estimate of the association, but not something that we have a chance to cover. But I do want to give you Googleable words. That's one of my general things here. Okay, how we doing? Hanging in there? Okay, your last question in the formative assessment for next week. It's asking you to list as many kinds of bivariate associations that we've talked about, and as well as test statistics and effect sizes for them. So what we've covered so far isn't very many on the list of possible pairs. But if we go through all the kinds of variables that there are, there's categorical and there's quantitative, right? As the two main kinds. Numbers are numbers in quantitative, and under categorical, there's three kinds. There's binary, which is only two categories, ordinal, which is three or more ordered categories, and nominal, which is three or more unordered categories. So in terms of all the possible combinations, we've talked about binary with binary, that can be Pearson. Binary with quantitative, that can be Pearson. Quantitative with quantitative can be Pearson. Ordinal can be Spearman. Ordinal with quantitative can be Spearman. Ordinal with binary could be Spearman, but I'm going to show you an alternative. The ones that we haven't hit yet are nominal. So we haven't really dealt with the categorical end of this very much, and that's what's headed next is going to be our friend chi-square, which is, wait for it, Pearson. He's back. Not just a correlation, but a chi-square. So have you guys seen these sorts of contingency tables before? You may have seen the tables, but not necessarily the terminology. So a contingency table is just the idea that you're dividing kinds of people into rows and columns. And this is what's known as a two-way contingency table because there's two variables being shown. You can have three variables shown in a three-way table, four-way table, and so forth. And so when you're dealing with categorical variables, you will often see associations in categorical variables described via this kind of contingency table. So vocabulary that goes along with this, these are rows in the table, these are columns. Each individual value is what's known as a cell. And we can compare the contents of the cells of these things relative to the totals across the rows or the columns, those are the margins, and use that to compute a measure of association. So if you have categorical data, no quantitative information, but mostly categorical, this would be the way that most people would tend to approach measures of association. Categorical data isn't something we're going to have a chance to talk about in this class, but there are other classes on campus, in particular in the stats department, that cover this, and I have readings I can recommend to you if you're interested in categorical data more broadly. But the chi-square is sort of a standard procedure, and so I did want to make sure that we had a chance to hit that one. But it's going to have to wait till next week because it's 1:42 by my watch. So you can say categorical by categorical is chi-square and ... to be continued next week on that answer, and that's totally fine with me. Chi-square is a different animal because you start by computing a test statistic and then work backwards to get an effect size, rather than starting by computing an effect size, which translates into a test statistic. So it's kind of weird. But all right. So questions before we adjourn? No. Okay, well, thank you for hanging in there. As always, thanks for coming. Let me know if you need anything. Hope to see your homeworks. Peace out. Stay safe, stay sane. Have a good weekend.